So Simo's up next, and this is why we sort of reordered, because actually he's going to, I think, do more nonlinear stuff with the Kalman filter, and tell us about nonlinear Kalman filtering and smoothing Bayesian inference in nonlinear latent force.
Okay, thank you, Neil. So yes, this is indeed actually continuation to my yesterday's talk about how to, well, because you can represent the Gaussian processes as state space models, and because, well, latent force models are natural differential equations which are state space models. So actually it's quite natural to combine them to get a huge state space model. And actually I'm explaining that in this talk. And I'm also going to introduce some things about so-called Ito stochastic differential equations, because they are the language which you see when you look at nonlinear state space models. And I'm trying to explain the basic principle, and so that you won't no longer be so scared of those Ito equations. They sound more scary than they actually are. There's quite a huge mathematical theory behind there, but you don't really need to touch that if you just use equations in applications. Okay, so first I present the basic idea, which is actually what I already said. Then something about stochastic differential equations or state space models. Actually they are almost, well, okay, you have ordinary differential equations and you can represent them in state space form. Well, that's the same kind of, in that sense they are the same thing. And then basics, what is the idea of nonlinear Kalman filtering and smoothing in this context? Because actually I have continuous models of discrete measurements, so it's slightly different setup than which Mike presented, but it's almost the same, because you can actually discretize, or, well, I'll explain the things. And then, well, actually I take one of the models used by Neil, I guess, and show how that particular model can't be converted into latent force or SDE model, and then the summary. Okay, but the basic idea first. So let's say that we have this kind of latent force model. Well, this is a first order model, so I actually don't recall, where did Neil go? He actually knows very much what this model's about. Where is he? Okay, we can ask when he comes back, so what was the actual basis of that model. Anyway, it's a first order differential equation which has some physical basis. So we have the process itself, and then we have the input force here. And so we measure this process xf at, well, discrete time instances, right, like this. And now we form the latent force models such that we set up because this is an unknown force function, so we set up a Gaussian process prior for that. And okay, let's say that we form Mattern type covariance function for the Gaussian process. We could use that squared exponent is quadratic covariance function, but well, this is nicer because we can use those state space methods easily. And okay, but yesterday I told you that actually if you have this kind of covariance function, you can express this as state space model. For example, if I choose this nu is half, this is simply so-called Ørsted-Uhlenbeck process. So I can actually say that this u is the solution to this stochastic differential equation. So it has this covariance function then. Okay, so I have a differential equation and I have differential equation, and well, I can combine them to get another differential equation, right? So now I have two-dimensional differential equation, and it contains, well, the differential equation for u is the second one, and the first one is the original equation. And then I can rephrase my measurement model like this. So I only measure the first component from here, and I call this h. And what I get is a model of this form. Well, I generalize a lot. So anyway, if we think in abstract terms, we have some kind of first order vector differential equation where there's a nonlinear function here and some matrix, and well, I had scalar white noise here, but now this is a vector of white noises. And the measurement model looks like this. Okay, but this is exactly the class of model that can be handled with nonlinear Kalman filtering and smoothing. So, okay, if I do this, then I just apply Kalman filter, smoother, and done. So, I don't need to, well, in that paper where this came from, actually the solution was, okay, I actually have a detailed example later, so actually, but yes, so another way of solving this is actually to try to calculate the covariance function of this, the solution of this nonlinear equation, and then, well, using those Green's function kind of methods and those, but this way we can simply convert that into state space model and then use nonlinear Kalman filtering and smoothing. Actually, I was confusing things a bit. Of course, that wasn't the actual model because I haven't written down the G there, but never mind. So Neil will have his chances to explain the model when I have the actual model there. Okay, so over here, well, this is called stochastic differential equation because we have, well, differential equation which contains the stochastic part. So there's a huge theory behind those stochastic differential equations, and I'm now trying to explain some ideas where they are based on. Okay, so first let's say that we have an ordinary differential equation, which is x vector, so this covers quite general class of differential equations, for example, all ODEs you get see in physics and so on. So you can actually, if you have a second order equation originally, you can just stack the time derivatives together, first order vector equation and so on. So this covers also like nth order equations. And then we add a white noise there on the right hand side. So we say that the solution or the equation is not exactly this, but there's a small, or not so small, noise term over here, which disturbs the solution. So if I originally had some kind of solution there, like this, what happens with that white noise present is that I might get, well, the stochastic solutions look like something like this. So they go a bit off from the deterministic solution. So I get some kind of distribution of solutions over here. Right, okay, and if I want to generalize a bit more, I can actually put a multiplier matrix in front of the white noise there. And for good reasons, I cannot actually put this white noise inside this L, because that equation is no longer defined, but it's a longer story. I will scratch the surface of that longer story in a moment. Okay, so now we have a stochastic differential equation in so-called engineering notation because we have the white noise there, and so it's not completely rigorous because I should have the Ito formulation. I will have it later in this talk. And in this context, this f is called a drift function because it's like the mean drift of where the process is going, and this L is the dispersion matrix, which somehow disperses the noise or diffusion, whatever. I don't know where the name comes from. Okay. And the white noise is a white noise, as you already know, I guess. So it's defined by so that any two time points are independent if the time points are different. So the covariance function is a delta function kind of, and I can put like an instant covariance there as well. Actually, this instant covariance is called spectral density. It's a long story why it's called spectral density. Okay, the long story is that the Fourier transform of the white noise is a constant, and in one-dimensional white noise has some number as spectral density, but the vector white noise has a matrix as the number which is constant over all the frequencies. So that's why it's called spectral density. That's the density of the spectrum, yes, or the height. And okay, this is a strange process because sample paths are discontinuous almost everywhere. Well, in practice they are discontinuous everywhere, but it's almost everywhere with like probability 1. And it's unbounded in any finite interval, and so it means that it takes arbitrary large positive and negative values at any finite interval. So it's quite badly behaving function, I could say. And okay, so what does the SDE solution look like if I return that? I had one example there, but for example, so-called Brownian motion is a solution to this kind of trivial differential equation. So actually, x is just the integral of w in some sense. So this is an example of Brownian path. So it's a random walk in continuous time. And here's one path of it, and this is the probability density, how it propagates. So it's the uncertainty like grows when time passes. Yes, so the right-hand side is the probability distribution or density. And another example, okay, this is the spring model, which is related to, well, latent force models, is that this is a second order differential stochastic differential equation where I have white noise over here, and so if I didn't have the white noise, I would have this black solution over here. But when I have the white noise, and different realizations bring different kind of solution which like drifts away from the deterministic solution slowly. And I could actually get nice animation out of this as well, so this could be moving. Oh. Okay, but anyway, this is a white noise right now. But why couldn't I replace that with something else? But let's go into that later. Okay, let's go through an example which is nice because this is a classic model used in practical target tracking. So it's a so-called Wiener velocity model, which you also find from, for example, classic book of Bars-Halom actually contains it. But okay, so let's derive a physical model for this car. So let's start from the Newton's law. So the force is mass times the acceleration. So actually what this says that if I have been given a force, I can solve the acceleration out of this, right? So let's model this force as, well, force divided by the mass as two-dimensional white noise process. So let's say that we don't know anything about the forces, so they are completely random in any direction and independent of time and so on. That's at least how it's explained in those books where they derive it. Okay, so those are the equations. But now I can actually write this down as, well, this is the classic way of converting differential equations into so-called state space form or first order equations. Just check the. So for example, the first part I originally had this kind of equation. Then okay, it was x. By the way, over here I use x's for various purposes and also y's for various purposes. So you need to, they are locally defined variables in this slide. So be careful in interpretations. Okay, let's say that we have this one. Now I can define that. Okay, let's say that I define another vector x. Now I'm using the local interpretation again. So let's say that this is the actual process, and then I define another variable called x2, which is the derivative. And now I can rewrite this as, okay, so this equation, if I use x2, this says that the first derivative of x2 is the white noise. And I need another equation so that the first derivative of x1 is x2. is x2. Okay, but now I can write this as, okay, I say that the derivative of the joint of these two, I can write down this in states, or not, in matrix form. So this is this kind of matrix times vector x. And then I have w. Okay, let's take one away, I don't need it. So it's this and w. So that's what I have done here. And if I do this for both of these processes and combine them, I get this kind of equation. Okay, and or just a linear dynamic system. And yes, and this particular model is actually called Wiener velocity model, but you can actually discretize it as well. But okay, let's not go into that yet. Okay, but now we can measure the car position. Let's say that we measure, well, the first two components in this model. These were the original position components, so I measure them. I don't measure these. So I can, well, write this down like this, or if I define a matrix H like this, I get a measurement model like this.
So just out of curiosity, did people ever try and learn the sparsity structures on those models to learn what sort of state space they need and allow a large...
So which part would you learn?
Could you, I mean, you always impose this structure which is giving you the gradient of x1, setting it to x3. But you could, you know, if you learnt that matrix in general, the values in it, you could you learn the structure of that matrix and therefore derive what the order of the differential equation or which state variables you need to represent the system. In effect, learn like the degrees of freedom parameter in the Matern covariance or whatever.
In a limited sense, you can do it, but the problem is that there exists like an infinite number of state space models which have the same like output behavior. So you can scale some variables and you still have the same model. So it's not identifiable. You need to put some.
So I was thinking of sparse type priors in order to do it. So I was thinking, assuming the scale doesn't matter, but actually what you want is a sparsity in parts of this matrix to know, so that you can start mapping some of these states to gradients.
Well, I'm not too familiar. I don't know if that has been done, but I would see some challenges in that. It might be possible, but I don't really know.
Yeah, I'm just curious.
I only know about like methods to estimate, for example, this A and L in some way. But yes, you need to have some constraints. Maybe the sparsity might be one constraint, so which makes it unique. I don't know. Okay, so in any case, we have this form of measurement model now, and okay, so what we have, this dynamic measurements models form this linear Gaussian state space model. Now, this is a slightly different state space model as in the, not the last, but the before that presentation, I mean, in the previous Kalman filtering presentation, because this is a continuous time model for the dynamics, and this is a discrete time model for the measurements. But actually, what you can do is that okay, let's take a look, because all SDs was the word which I was looking for. So all SDs are stochastic processes which have a transistor density. So actually, what you can do is that if you have the process which is a vector and you measure it at some places, so what you can, because if you're only interested in the posterior distribution of the measurement points, you can actually solve the joint distribution of these points by integrating away these parts. And the transition density is actually the distribution which gives, like a given that I was here, what's the distribution of the next one? Because the system is Markovian, that actually defines the whole distribution. And it happens that actually in this case, this is a linear SDE, you can actually solve these matrices very easily. This is actually matrix exponential of A times delta T. Just
as far as I know, phi k, I think you can't simply write phi k times x ck minus 1. I think phi should be something like e to the power of at.
Yes,
and if you do some simplification, like Euler approximation, and you got the linear function that the discrete time one.
Yes, as I said, that this is the matrix exponential, and it's the exact answer.
But what I mean is that the x is in the exponential. You can't separate.
But you can write it down as matrix exponential.
Okay.
For example, I can actually calculate it. For example, for this model. That's high school stuff, I could say. So.
Not in the UK.
Well, not in Finland either. But okay, so the matrix exponential of this matrix T. So, okay, so you said that actually this can be calculated in closed form because, well, matrix exponential, if you write down the Taylor series expansion, so it's just the identity matrix plus this matrix times, let's call this, okay, it was A actually, our model. A, T, and then we have half times A squared T, and so on. But actually, if you calculate this A squared, you notice that this is 0. And you get the result that actually the matrix exponential is, well, you have identity matrix plus this matrix times T. So you get T 0, 0, T 0, 0, 0, like this. I think you saw this in Mike's presentation. And I can actually write down the equation for, well, for that other matrix as well. It's more complicated, but in principle you can actually calculate that. Yes, so that's psi. And for the W, you actually see it in very signal processing books. It's actually, okay, if this was a psi t, it was something like this as L, and then you need to have a spectral density T minus S, like this. Actually, you integrate from over the delta T. So this is the W. And actually, given this, you can even compute this. I'm not going to confess that I recall it by heart, but I do. But it only contains polynomials which you can actually integrate over. Yes, but in general you cannot express the matrix exponential in closed form, but for many practical models you can. And actually you don't need to be able to express it in closed form because you can always use MATLAB's or R's or Python's matrix exponential function to actually evaluate it. Yes. Okay, but of course we could also start, well, go back to the beginning. This was our Newton's law. Let's say that those forces are not white noises, but they are, well, matter 3/2 processes. And well, from yesterday we recall that actually these matter 3/2 processes can be expressed as state space models of this form. So if I say that U vector is a solution to this stochastic differential equation, then this first component here will have the Mathern 3/2 covariance function. Okay, so now I can do the same thing, and I will get, well, my state components will contain the original ones as in the white noise model, plus then the, well, for both components, the Mathern two-dimensional things. And I only need to work out what kind of matrix here I get. It looks big matrix, but it's, well, once you have it, it's just constant matrix which is there. You can write a small program to actually form the matrix. And the L will look a bit different, and you have two additional noise processes which are related to the Mathern covariance function representation. And the measurement model, well, this is a slightly bigger matrix because you need to pick these two things there. But in principle, you can call this H. So it's still linear state space model. Okay, now you can apply the Kalman filter and RTS motor, and you have the result. So that's the basic idea. But this is a linear model. So this is like a linear latent force model, I guess. Of course, you could start from spring model instead of the Newton noise model to get some other, like second-order systems, I guess. Yes. Okay, then something which you often encounter in SDEs is all this ITHO calculus. So I try to explain some principles and definitions or something. This is not a this is just a brief introduction to the idea, so that it doesn't sound so scary anymore. Yes. Okay. So let's take a look at this, well, one-dimensional version of this equation which I had. The general form. So this x is a one-dimensional. This is some nonlinear function, and this is some nonlinear function. And this is white noise. Okay. But now if we integrate from, I have actually integrated from s to t. So we get that, well, xt minus xs is equal to integral of this delta t, and integral of this kind of term we have L times white noise times delta t. This is actually how you define differential equations also in classical calculus. So then you define this as a Lebesgue integral or Riemann integral, and this also as Lebesgue integral. But now the problem is that actually this is fine. This is like a Lebesgue integral because this is a continuous function. But we have the white noise. Okay, it's discontinuous everywhere, gets unbounded values at any finite interval, and so on. So we cannot actually define this integral as Riemann integral, Stieltjes integral, or Lebesgue integral. So it doesn't work. So it means that this is not a defined differential equation at all. So the whole idea of ITHO was that actually, let's take one step backward. So let's pretend that we didn't have a white noise in the beginning, but instead we only consider this increment, and say that this increment is an increment of a Brownian motion, which is the, I had it, it's like an integral of white noise in the engineering sense. Okay, let's say that it actually originally is like this, and we rewrite this second integral as L times delta beta, which beta is the Brownian motion. Also in Stieltjes integrals and Lebesgue integrals, you see this kind of notation, but you have the measure, like delta measure over there. And now it's kind of stochastic measure if you want to go to that path. Okay, but now we can also use shorthand notation. So let's say that this t minus s is, or s minus t is quite small. So this is delta x, and this is f times delta t plus L times delta beta. So this is the notation which you see in stochastics books. And it's the reason because you cannot really define these equations as differential equations as such, but you need to define them through this integral equation. And this is also the reason why you cannot put white noise inside here, because the white noise as such doesn't exist. And you couldn't convert that into integral equation if you had the white noise too non-linearly in the equation. But actually in stochastics, you see this same equation in this form. So usually they prefer the random variables as capitalized, and t might be here, and there's also this is stochastic process which is function from event space to functions, right? And then it's usual to denote those. I hate this notation because it confuses. But you can always like lowercase your letters and take away the omegas in your mind. Okay, and so, well, we can actually check how that Ito integral then is defined. So it is defined as this kind of sum. Well, also in normal like Lebesgue integrals actually use this same thing. So you define the integral as the limit of this kind of sum where you have the argument here times the differential argument differential. And now the ordinary integrals are defined so that this t over here is selected to be, well, any value in the interval. And actually the definition of the integral is that it converges if it's independent of the choice of this value on the interval. Okay, but in Ito things, this actually depends on this small choice in the integral, and that's what it was Ito's idea, to actually use the beginning of each of these intervals to actually get a good definition of the integral. And yes, as I mentioned, so in these classical ones, it's independent of the evaluation point. And now you also sometimes call, well, this is called Ito calculus with what you get out of this definition. So you can actually derive the whole calculus from this small thing. And it's
enjoying the fact that I spent this morning explaining integrals to my son, and you're spending this afternoon explaining integrals to me. And my son's going to be a bit confused when I start trying to introduce Ito integrals this evening.
Okay. You can borrow my slides.
Yeah, that's why I just took a photo.
Simo, so you wrote down the simplified version on the slide before, sort of handy for notational convenience. I think it's called the Ito someone form. I can't remember the d beta. Yeah. Well, the first one at the top actually, the d beta equals w dt. The first equation there.
Yes.
Sorry, at the very top there.
Yes.
Yeah. What's the best way to think about that? Because naturally, from normal calculus, you'd say that the rate of change of Brownian motion with respect to time is white noise, but that's not quite true anymore because it's a different Ito calculus.
Well, actually, in principle, or in your mind, you can actually divide by delta t. So what you get is that the derivative of beta is white noise. Right. So in that sense, actually, white noise is the differential or derivative of Brownian motion. But yes, but it's not. You cannot really define these equations through that path.
So in what sense is that shorthand?
This one.
In what sense is that a shorthand?
For this.
It's just you remove the integrals and
yes,
the difference with the d.
But it's as valid as a statement.
Yes, it's like a differential form because these are like infinitesimal kind of things here. It's not true for any finite like a difference, but it's only true in the limit. Yes?
Can you go back one slide? So what's wrong with just saying that I have a distribution over W of t, say a GP over W of t, and just treating this as a probabilistic statement. So I could take a delta function as my expression of this statement, say that my distribution for x of t minus x of s, given knowledge of W of t, is the integral on the right hand side, and then just marginalize against my distribution for W of t.
You're forgetting that you need to define what you mean by integral. So you need to go to the lower level. So what do you mean by integrating?
Right.
Yes. So you mean Lebesgue integral, right?
And what fails in using Lebesgue integration?
So what fails is exactly this. So in Lebesgue integrals, when you integrate over a measure, you need to have this integral independent of the...
I don't have to integrate against a measure anymore. Like, the W in the integral over time is only ever an instantiation of the process.
Okay, but you cannot define the integral for like a discontinuous everywhere function either. So it's...
Because it's varying infinitely quickly, I think.
Okay.
So it doesn't... Is that right?
Yes, it varies too quickly, so you can't really define that.
Why is the latent force model not a stochastic process? Because W of t is continuous and not varying infinitely quickly. So this integral is well defined under any of those. If you use a continuous, like exponential quadratic for W of t.
Yes, that's very well.
As delta t changes, it just goes up and down.
But it seems like in expectation only you have to worry about the mean, right? Which will be continuous.
But expectation is an integral and the mean is obtained by integration. If you cannot define the integration, you're stuck in that level.
But for the expectation integral, I can just use the Bayesian integration.
Which integration?
The Bayesian integration.
But it's not defined for this.
But in the expectation,
this quantity as such which you're calculating the expectation of is not defined, so it's like a...
The function W, right? And the way it's written there, it's not its covariance, it's not looking up. It's like...
It's true that
the distribution is also you can't even define these images.
Yes, it's true that it's not function in the like a classical sense. That's the problem.
Yeah, in the way that like I draw it for my sons. In terms of you sort of try and close the box down of the delta t's, right, to get the integration. The thing that you've got white noise right on top that's varying infinitely quickly, sort of going up and down across. So as you close that box, you're not actually getting any. There's no smooth function that you're actually. I mean, that's my instinct. It's just sort of.
Yes, so it is.
There's an empirical explanation of that. I mean, if you see the power spectral density of this W, I mean, engineering sense, I mean, it's a flat, but I mean, it's when you sum up to that, it's infinite. How you can work with that infinite power?
Yes, it's true. In any like finite interval, you have infinite power in that. Yes, it.
But in continuous time, what does that mean? I mean, if you empirically assume that okay, there is an infinite power spectrum, and how to integrate it?
Well, that's another. Okay, so that's an interesting question. I mean, that's a convolution, right? So we can ask the question: what happens to that convolution in Fourier space? And then it should be the product of the Fourier transform of those two things. So how do things fall apart then? Is it because this power spectrum is flat and is not?
Well, if you put white noise through a linear system, you will get the constant times the linear system's response. So if it's a low-pass system and it integrates to finite number, you're fine.
Yeah.
So actually you can reduce it into finite power system like that. But of course you need to remember that these are nonlinear systems, and non-stationary systems. So there exist Fourier transforms, but they are not very useful. Okay, so this was the form in stochastic literature which you see. And okay, so this is the source of the problem. And actually, well, sometimes you encounter some other versions than Ito calculus, and it's exactly related to this integral definition, and it's related to the second part of the SDE. So for example, Stratonovich integral is that you choose the middle of this interval. So you get different kind of rules for calculus, which is strange, but that's what happens. And you see these kind of equations. So you put this circle there. And this is the definition which you like, because you said that you want to think white noise as the limit of like a smooth processes.
Yeah. So what I do when I think about integral, because I understand Ito calculus, is I assume it's an infinitely smooth Gaussian process, and I assume I'm going to do that convolution and then take the limit of that infinitely smooth Gaussian process as the length scale goes to 0 after I've done the convolution, which seems to me...
It converges to Stratonovich
Simo's saying
SDs.
that leads to Stratonovich SD, not the Ito. So
Yes.
I'm a little bit... Now there's still something I don't understand.
Well, so there are two integrals going on here. One's over time and one's over the value of the white noise process, right? Like, it seems to be conflating two things here, and that's why I'm confused. Like, so we have to marginalize over what the actual instantiated values of this white noise process are, and then we have to integrate over time. And I'm getting confused as to which of the integrals it is that we're trying to solve for.
Well, you're marginalizing something, but I'm not. This is like the path space. I'm not completely sure what you mean, or what's the problem.
Why isn't it an integral over time?
I think there's a misunderstanding. So there is no marginalization over the values of that random number. It's actually a distribution.
The integral's random.
So, okay, this is describing a distribution itself, right?
Yes. So yes, these are random functions. If that clarifies anything, I'm
so
sure.
they're being left as random variables.
Yes, they are random still. Nothing has been. We haven't calculated any expectations or anything.
I think also part of the confusion is because it actually doesn't exist. Like physicists have dreamed it up. It's all based on the Wiener process, and the Wiener process is something that is actually discrete that happens, and then you say, okay, what if it wasn't discrete? And so I think part of the problem is arise from just this mathematical trick that was designed to almost something in the real world, but then everyone already knew it didn't exist. It just makes calculations easier. If you dream up a function that's not a function, and if you define a function that doesn't exist but just something you want to hold true about the function that can't exist. So this WT doesn't exist. It just has properties. It's just something that, if it existed, had certain properties, and hence you can't optimize it. You can't really apply T into W. It just doesn't exist.
Yes, and that's also a hard question. Does it exist or not? Well, no mathematical object exists, but yes, it's true.
Okay.
Please.
So if we haven't done this marginalization integral yet, we have to eventually, right? Like at some point we have to marginalize over what this noise process is. And when we do that, why don't we just take the expectation, which is going to be 0?
Yes, we will, but actually, if we just treated that white noise as an ordinary function, we would get wrong equation. So you need to use the rules of that Ito calculus to actually get the right solution.
But at the point that I marginalize over the noise process, I sub in the mean, which is going to be 0. I don't have to worry about using calculus.
Yes, so you would think that the mean would be 0, but the trick is that it isn't. So,
Philip has a point.
so if you calculate the mean of this, this has 0 mean and it's independent of this, but this mean is not 0. That's a very strange thing, but that's a conclusion, or it comes from this definition. So it's very strange, but anyway, you will have a correction factor there. For Stratonovich integral, it is 0, but for Ito, it's not 0.
So then I have to modify both my integrals, because you're saying I can't even take the expectation the way I want to. As soon as I do that, I'll get 0.
So you cannot change the order of integration, so you cannot put the expectation inside this integral. You might remember from the mathematics courses that you need to have some kind of property where you can change the order of integration, and this doesn't satisfy that.
So just on Jan's point about this function not existing, and one of the things I found helpful was thinking of something much simpler, which is the impulse response, right? So you can drive a system with an impulse response, which means putting a delta function into the input. Delta functions don't exist. There is no function of finite space with infinite height like that. It's just a really good approximation to hitting the system with a hammer, because what you're doing is you're putting something into the system whose the time at which it operates is much smaller than how the system responds. So as far as the system's concerned, it's equivalent to a delta function. And I think that's the same thing when you think about the Brownian motion origins of like pollen being hit by water molecules. What that's saying is that you're getting many impulse responses. The water molecules hit the pollen in 0 time with each impact, but finite energy. So you've got these continuous And that's how you end up with this. So it's like many, many impulses. I mean, I don't know if that's a good way of thinking of it, but in the same way that the impulse response doesn't exist, I think that's what Young was saying, yeah? This is a mathematical construct that makes computation later easy, in the same way that the impulse response, being a delta function, makes computation easy.
And it comes from gas modeling, right? I mean, it's called the increments are called Wiener process, but they're also called Brownian motion.
Yes.
That's because it's used to model these atoms. And as you said, it's modeling hitting with a hammer, but hitting continuously with a hammer, which is why, because you can't even imagine that it's possible, right? It's possible. This is why it's so not intuitive, and that's why you need to just model the increment of what would happen if I were continuously hitting with a hammer. From different sides and angles and continuously.
But another way of thinking about that is just thinking about a smooth continuous process that is just fluctuating so rapidly while its energy stays fixed. And as you take the limit of that, you get the white noise process again.
So which calculus does that work?
That's what confuses me now, because Simo says that. I thought, okay, that's fine, that must be the Ito calculus. But Simo says, no, that gives you the Stratonovich calculus.
Well, I can actually try to explain the thing. So this is actually what you get if you think about like a delta function, which is like symmetric with origin. Because you put this in the middle of those things. But the disadvantage of this is that actually you're like looking in the future, because you have that delta function reaches the left-hand side of time. So you have like you're ahead of time in that sense. So in that Ito version, you shift that delta function a bit so that you're actually just after it. So you are not looking at the future. So you have the increment just out of that. And that infinitesimal change affects the results. That's the thing. That might be one way to think about it. Yes?
Does that mean that I can't simulate the Stratonovich equations unless I firstly convert them into Ito?
Unless you have a method which treats them as Stratonovich ones. But okay, you have to notice that actually I have L depends on X. And very soon I have a relief of this thing, because if L is constant, then this Ito and Stratonovich are equivalent. So actually, for example, in my car model I had constant L. So I don't need to worry about this at all. But in principle, this thing exists. And for example, if we calculate the covariance of any process, you will have like multiplicative terms, and you will need to take into account these strange things which are happening. Yes, so as here. So for example, in mean and covariance equations, you get a different result than what we would get if you just calculate it like a normal expectation just by using the normal calculus rules. You get different result. Also the distribution would be different what you get. So it's good to know that these things exist, but of course in practice you rarely need to worry about them.
Apart from existentially.
Okay, but anyway, so what kind of solutions SDEs do you have in principle, and where they are used in state estimation contexts? Okay, part of solution is that when you draw white noise, or I don't know how we would represent white noise, which is not even a function. Okay, but when you draw a Brownian motion and then you simulate or calculate the solution of the ODE. Yes, so that's like a Monte Carlo simulation of SDEs. And in particle filtering or smoothing, you can actually use that directly, because you want to sample the paths. And then you can derive the distribution of the solution. So given, well, when you have many W's, or however you want to think, so this P xt has some kind of distribution, or it has joint distributions. And the solution is called Fokker-Planck equation in physics, and Kolmogorov-Forward equation in statistics or stochastics, and I'm sure it has other names, but anyway, it's a partial differential equation which gives the distribution. And it can be used in some basis function methods and grid-based methods in state estimation. And in Kalman filtering, the mean and covariance are of interest. So actually, we can derive from the Ito calculus the mean equation and the covariance equation, which are ordinary differential equations for the mean and covariance. In non-linear case, they are not solvable, but in linear case, they are, well, they're just linear equations, or actually linear and kind of Riccati kind of equation. And okay, so in nonlinear Kalman filters or Gaussian filters and smoothers, they are used. Actually, this is one term in like control. Anyway, in that context, actually, the term used for nonlinear Kalman filtering is sometimes Gaussian filtering, which might confuse some people working in image analysis, because Gaussian filter has definite meaning there, but it's different. Again, some locally defined terms. Okay, but one property, okay, so Ito stochastic differential equations or their solutions are Markovian, because actually, well, the distribution of x, t, k, given the path after that, well, actually, I have up to the previous measurement point or something, is that the history disappears and we are only left with the last point at the interval. So it's Markovian. And there's a complicated reasons why it's true, but it's related to the martingale property of Ito integrals. And actually the expectation of any Ito integral is 0 if you look at carefully. And so because it's Markovian, these transistor densities actually define the whole process. So you can actually write down the joint distribution of any finite number of points in terms of the transistor density, because, well, they are Markovian, so you can just write that down as a product of these. And this transistor density is actually the Green's function of this Fokker-Planck or Kolmogorov forward PDE. I should have the PDE actually in some later slides. Yes, okay, so, and the Kalman filtering and smoothing is a methodology which can cope with these models. So it was originally like developed for these kind of models. Okay, so the way of thinking of these systems is, okay, so we think that we have a time here, and this is the signal direction. So we have some kind of signal going here in time, which is continuous, and actually this is the derivative of the signal as well. But okay, the original signal is continuous, but we have some discrete time measurements made out of the signal. I have drawn like a uniformly sample, but it doesn't really matter what sampling times we actually have. So this is called continuous discrete, in parentheses, time state estimation problem. And so we estimate unobserved continuous signal, which is called state, from noisy discrete time measurements. And the mathematical model, well, I already introduced you to the Ito notation of SDE, so this is that one. So you can also think it as, I have the white noise form here. The measurement model, what I'm considering here is a linear model. So it's some matrix times x. For example, in my car model, I had that kind of linear model as the measurement model. And okay, the dynamics are modeled by this Ito equation, which might come from physics plus the matter and covariance function as the dynamic model form or whatever. And so these are Brownian motions, which are also called Wiener processes, which I forgot to mention. And this is a Gaussian random variable. And okay, I already covered this, so we can think this SDE is a white noise driven differential equation. So in practice, it's actually much easier to like formulate the model using this, and then you multiply by delta t from both sides and are happy. Okay, so what's the idea of Bayesian filtering and smoothing or Kalman filtering? Well, Bayesian filtering. So we don't want to try to, or we would like to compute the full joint distribution of the whole process, but we don't really hope to do that, because if you think what we would need to calculate is So our process is here, and we measure it like this. So this is xt. Okay, so if you first think what we have, say at the measurement points, so we can actually define xt1, xt2, xtn measurements. So we could actually try to calculate this kind of quantity. This should be feasible. But that's not the whole thing. We actually want the whole process. Also, we are interested in interpolating here as well. So now the question is that how should I actually write down even? So I should put the whole function here as the argument. So even the notation breaks down. So it would be like infinite dimensional distribution of this whole thing somehow. So you can actually show that if you keep certain things constant and take the limit of infinite number of random variables, you will end up having a 0 or infinity or delta function or something which doesn't really make sense. So that's why quite early we give up that approach and take another path. So instead of actually trying to compute the full thing, we concentrate on calculating the marginals, so that with given a fixed time point, we want the solution at this time. Well, if this is a Gaussian regression problem, this would correspond to predicting the value at given point. So that's quite fine. Actually, this is only, okay, the filtering solution is only conditional on actually, well, you had introduction to Kalman filtering, so it's like a causal conditional distribution. And you need to compute the smoothing solution to have the full posterior distribution or the marginals of the full posterior distribution. So filters calculate this kind of solution. I could actually draw it. So filter, when you start from here, and at this time point, you have the filtering distribution given the measurement. So it's conditioned on the time points before that point. So it's always just you can calculate, well, between these next measurements you can actually use the prediction. So that's the filtering solution given the previous measurements. But the smoothing distribution means the batch solution. So you condition on all these measurements and you can calculate at every place here the distribution of this given all the measurements. Yes?
We use an interval. So, I mean, xt is a value at a particular time point, or is it within that interval?
Okay, sorry, I have my I have defined all the notation, yes. So, in my case, I had, so this is from 0 to t, and k is somewhere in the middle, if you refer to that. And those T1, T2, T3, they are some time points on this time interval. Yes, sorry about not defining that. Okay, so if we could solve the transistor density of the SDE using that Kolmogorov forward equation, for example, then this would reduce to discrete time state space model of this form. And of course, this is the one which is handled very well with particle filters, in principle, at least. And also discrete time Kalman filters can be used for that. And for linear Gaussian systems, well, I had an example that the car model and also the latent car model were linear Gaussian systems of this form, and you can actually use Kalman filter and RTS smoother to those. Okay, but anyway, from going to SDE path, we can return back to this one because this is what we really get out of that. But the catch is that actually, when the system is nonlinear, we might want to use the continuous time mean and covariance equations in the end. And actually, that's what we are going to use. Okay, so we can actually write down the formal Bayesian filter for this kind of continuous discrete system. So we have SDE and some measurement model. So it looks like this. So we loop over measurements, and we always do prediction step, which we actually need to solve this ugly looking partial differential equation. So we start from the previous step and solve the equation on the next time step. So we use the initial condition is the previous distribution, and then we solve that. So instead of like propagating mean and covariance, we need to solve that full equation. And then on the update step, we use the Bayes rule, as in the Kalman filter. Or, well, Kalman filter, you have the Gaussians, so the Bayes rule reduces to certain simple computations of means and covariances, but the general case is the Bayes rule. Okay, but as always in Bayesian computations, this is just a formal thing, and you need to approximate anyway. You cannot really use these, except in the linear case. Okay, so Kalman filter is one way to approximate those, and it's based on using Gaussian process approximation or Gaussian approximation. It's actually this quite confusing term because, well, it is since if you linearize the system and just propagate the mean and covariance, it's a Gaussian process approximation, right? Yeah. But it's not exactly in the same sense as you use it in machine learning things.
But Manfred does quite a lot. Manfred Upper on or has these weak noise approximations.
Yes.
And Darren Wilkinson has these approaches, and I guess they're all Gaussian process.
Yes, and that's actually Opera uses the same Gaussian process.
Yeah.
Actually, we have been looking at the connection between like this more classical Kalman filters and smoothers and those so-called variational ST approximations. Yeah. I think they are quite much the same thing. That's my conclusion.
That would be good to give them less things to learn.
Yes, that's nice that people unify things, so you only need to learn that one thing.
Learn one thing, yeah.
Yes.
Yeah, so the solution for your SDE for the X will be your transition distribution you used for what?
Could you repeat?
Sorry, so the solution for the first ingredient for this SDE for X will be your transition distribution from xt minus 1 to xt.
Yes, so it models that, if you mean that. So in that sense, yes. So yes, I get the measurement of the process, then I follow the SDE until the next time point of measurement. I measure it, follow the SDE, and so on. Yes, so this Gaussian process approximation leads to nonlinear Kalman filters, and actually nowadays Kalman filter is usually like written down for discrete systems, so we have some kind of discrete time dynamic system. But actually, originally, the more common one which you find in older books is also in the original article of Kalman is actually this continuous discrete version. Well, in Kalman's article, you will find a solution to an ODE system in terms of transition matrix, but okay, so it's not exactly continuous discrete form. But for example, Jaczynski's classic book treats or talks about this kind of models. Okay, and actually we can generalize this linear into non-linear, but it's easier to write down the equations if I have the linear case. Okay, so the approximation is, well, this filtering distribution is approximately Gaussian, and these will be computed by the nonlinear Kalman filter. And there are different brands of Kalman filters.
for the GPLVM. I was slightly surprised you don't get the covariance.
Yes, it's not even in the field of prediction equations. They didn't contain.
Sorry, Simo, could you repeat the question? Yes, could you speak?
So the question was, I was sort of looking for the expectation of f of x transpose, the covariance under a Gaussian of f of x, but it doesn't seem to arise apparently. I thought that would be in there too.
Yes, it's not here either. You only have these cross terms.
Perhaps somehow it disappears.
Yes, okay, so one way would be to use particle filtering, but that's another way, and it has its good sides and bad sides. Okay, and then actually I already advertised that I would have your model in the beginning, but actually it was only over here, so luckily because you were away for the couple of first slides. So actually the model, so it looked like this. So what was actually the physical basis of
this? So what was that saying?
So what does it model?
Right, yes, the nonlinear latent. So the that one is it's a first order differential equation. It's for systems biology. So in this case, do you want me to do it? X is gene expression. So it's like data we have the machine for acquiring downstairs. So X is a gene expression time series, and that's easy to measure. And U is a protein that's switching on X. So you've got, this is a transcription factor, and this it acts like as a switch to switch on different gene expressions. But because concentrations don't normally go negative, then you need a nonlinear, you can't just put a GP in here, allows concentrations to go negative. If you just have one of these, you can get away with it because the data keeps it positive. But what we were interested in is having more than one transcription factor controlling the genes and working out which proteins are binding to which transcription factor. So you're interested in this S matrix here, who's connected to what, and you observe X, and you want to infer U, which is the transcription factor, and learn S, which tells you which genes are being affected by that transcription factor. So you unpick the genetic network. That's the explanation.
Yes, thank you. So, okay, that's the physical base. I was expecting that because otherwise I would just say, okay, we have this differential equation. I don't remember what this really means.
Well, and the other thing about the nonlinearity is the transcription factors combine in different ways. People have different models, so that could be. So he's written it. We use Hill functions and various functions in the nonlinearity. It could be various different nonlinearities. People suggest different things.
Yes. So this was treated in this our article, which was it's exactly about like nonlinear state space model representation of LFMs. So okay, so the procedure that this is almost directly from that article actually, and the notation is also from them. Okay, so we model these as independent Gaussian processes, and okay, so these are well, it's just mean and covariance function. But okay, let's say that let's recall that if we have a say Matern covariance function with say 5/2 parameter, then we can express these as solutions to certain SDEs. Okay, let's now assume that we actually have chosen such. And in general form, what we get is that this U's, if we collect this, just a moment. Yes, this should be Z actually. So let's call Z is the vector of these U's. So we can represent it as a solution to certain SDE, linear SDE, where this vector contains all the components. And okay, so this can be formed like this, and L will look like this. Okay, and then, okay, so if we combine it with the original model, which can be written in this kind of generic form, so we get two. This is an ordinary differential equation written in the compatible form. So if I multiply by delta t, I can write this like pseudo-Ito form equation without noise. And this is the other one which models the U parts. This should be Z as well, by the way. Well, U is the first component of Z, but I should use either Z1 or, but you get the idea. Okay, then, okay, so I have M state components there, and these are the latent, Z's are the latent force processes, and F is the dynamic model corresponding to the original LFM. Yes. Okay. But now I can combine these processes into huge vector to get one SDE, which contains both the Gaussian process priors and the actual LFM. And then I can actually assume, well, I guess it was linear measurement model in the original article, but I could actually use any nonlinear measurement model which I want to, and still keep within the framework. And now we can apply Kalman filter and smoother to this particular problem to get the state estimates, which also give us the Gaussian process predictions, or the predictions of the process anyway. And there actually exist also parameter estimation methods that can be used for estimating parameters in these models, which use Kalman filters as like components in the methods. Okay, so the summary. So nonlinear LFMs can be converted into state space form. Well, we first convert the latent GPs in the state space form, and then we just stack these processes into one system. And this Bayesian filtering and smoothing, in principle, provide the full solution to the problem. In the details, there are those Ito things that you need to be aware of when you work with continuous time processes, but they are quite much under the, how do you say, you can think them as like black box. You don't need to too much touch them if you don't want. And okay, this formal solution is intractable because you would need to solve these partial differential equations, actually very high dimensional. And so that's why you need to approximate, and one class of approximations are these nonlinear Kalman filters and smoothers. Okay, thank you. Yes, there are those differences.
So we've got questions and I think discussion scheduled now. So let's use questions to maybe start a bit of discussion. Questions? You.
It's an audio process. We will take the same form for Ito's catalyst and Stratonovich catalyst.
So it will take the same form as
the Stratonovich.
Yes, the Ito and Stratonovich SDEs are the same if the L matrix is constant, right, which I do have if I have a.
For you, because the L is constant, so they are the same.
Yes, or actually it can depend on time, but if it doesn't depend on the state itself, then this Ito and Stratonovich forms are the same.
Can I have, no, really silly question, as well as just having Brownian motion, can I have like fractional Brownian motion to drive these differential equations?
Yes, there is work on those, like using Brownian motion driven SDEs. The challenge is, well, actually, yes, you can have anything which has that martingale property.
So fractional Brownian motion, that's not.
Yes, I think that might be a challenge, but I have seen papers about like defining. Well, actually, I know one researcher who has been like introducing those to SDEs. So it is possible to define those. Of course, well, you can define anything, but I don't know how you get the actual practical solutions out of that. Yes.
It's going to come out very garbled, and I'm not quite sure what I mean. But so the problem we have, we want to estimate the parameters in the dynamical system.
Okay.
And in order to do that, I thought we needed the smoothing, the positive distribution of the trajectories. And you did it just by taking the marginal slices through to get the filtering and smoothing distribution. But you're still able to estimate something about the trajectory. So I'm wondering what's failing in our thinking that makes us believe we need the trajectories in order to do this.
We don't need trajectories, actually. So the parameter estimation is based on, like, it's called prediction error decomposition, which gives the likelihood. So it's, I hope I recall it right. So it's a, like the marginal likelihood of whatever you would like to call this, can be written as like product over, well, you have a yk given y is from 1 to k minus 1. And these can be expressed as yk, okay, of course, theta here. 1 to yk minus 1 is because of Markovian and those properties. You have well, conditional independence and Markovian. This is the measurement model, and this is the filtering. This is the filtering distribution, and this is the measurement model. So once you know the filtering distributions, you can calculate these terms, and you can calculate the likelihood. And of course, all you need for parameter estimation is this, because you can form them. Well, the posterior is just well proportional to prior and this one. Was this something which you ask, or?
Yeah, I mean, we wanted to do it by avoiding this likelihood calculation because we don't know the likelihood of the simulator, essentially. So we want to do it with just particles, sample trajectories, and we want those to. So maybe we can do it this way by forming that approximation to the likelihood, but we wanted to avoid that if possible. But that makes sense.
Yes, and for example, so-called particle MCMC is based on exactly that one.
Yeah, absolutely.
So you actually simulate trajectories, so you get Monte Carlo estimate of the filtering distribution, then you calculate Monte Carlo estimate of this, and then you plug that into MCMC methods, that approximation, and that's for some reason it actually is valid MCMC method. So the approximations cancel out somehow.
So actually all the derivation has to be based on the assumption that the noise is a white noise. So in case it's no white noise, does that mean particle filter actually has its advantage there? Since particle filter doesn't have to assume the noise is a white noise.
You need to have a Markovian system in particle filters as well, and the whiteness of the noise ensures that the solution of the SDE is the Markovian process. So in that sense, if you had non-Gaussian, non-Markovian or non-white process driving the SDE, you wouldn't have a Markovian solution, and you couldn't use the particle filter either as such. So the white noise thing is really a mathematical trick to get that Markovianity to the system.
I wanted to ask about something Mike mentioned in his talk, is if you've got some sort of sensor dropping out over a certain time, that's kind of trivial to deal, well, depending on how you set your model up, it can be easily dealt with a Gaussian process. Is it straightforward to deal with that, one sensor sort of disappearing within the state space representation?
Yes, so if one, well, okay, there are like two things which you need to take care of. First, is that your time between measurements changes, and also your measurement model changes. But actually, in more general form, actually, you can have like even in linear case, your measurement model can depend on time instant. So you can actually change the measurement matrix, or you don't need to measure at all at given time step. So you can actually just skip the measurement update.
You can skip them. You can skip them partially. So you can skip them for some sensors and not others.
Yes, you can just take the couple of first rows from the H matrix.
So you don't need to do what I think can be a really bad thing. If you get into a situation where actually most of your data is missing, the thing I think you want to avoid is like a data imputation type algorithm like EM. And here you don't need to do that, because that's a nice thing in the GP actually. If you start losing an enormous amount of data, you just ignore it. You don't need to impute it and fit the parameters as you do in most models. And the same thing.
Yes, you don't need to, because you can just define the measurement model differently. So you have only one sensor at that time
you drop
instant.
it because the model's consistent under marginalization, basically. In this, Questions? And then we can also move into discussion. So I could try and start the discussion with a provocative question. What's all the point in this? As Bishop used to say to me when I say something, he'd say, "So what?" So I obviously believe there's a point. So what do we all find it? What are we going to gain? What do you think we can do with these methods that people haven't been able to do before? I guess is the question.
Well, first of all, these are linear in the number of time steps, which is one thing, and because when you have a non-linear LFM, you have very much difficulties in you need to solve the closed form solution to the ODE, which is not possible usually, and then you would need to, if you use that Green's function method, you would need to somehow propagate the Green's functions through that non-linear, or anyway, you need to calculate the covariance of the solution or approximate the solution somehow, and that can be quite tedious. And this is like a generic way of treating all those without those particular problems. Of course, the approximations are different, and it might not be, because anyway you need to have good filtering approximation to get good smoothing approximation. So the possible weakness is in that. So they might not be good always.
So you have some parameters in those models, yeah?
Yes.
So for the differential equation, for example, you have the S and you have the V, yeah? How do you treat those parameters here? I mean, because in GPs you use some sort of hyperparameter learning.
Yes.
Here,
it was which I wrote here. So for example, in GPs, you can actually derive this marginal likelihood in closed form, or it has simple expression. So for the Kalman filter, you get, given the Kalman filter in Gaussian approximation, you can write down these quite easily. So it will be kind of, the log likelihood is some kind of quadratic over the Kalman filter results. So for given parameters, you can run a Kalman filter and you get the marginal likelihood in the end. So you can evaluate one point or one particular value of this by running a Kalman filter to the thing. And you can implement MC or optimization over that approximation.
Actually, you can also draw the derivatives of that, which helps a lot if you try to optimize the parameters. Simo has been working on that as well.
Yes, it is true that because you have the Kalman filter, you need to run the Kalman filter to even evaluate the likelihood, but you can actually differentiate the Kalman filtering equations to get additional equations for the derivatives. You're going to propagate them to the end and get the derivatives of the log likelihood.
That's a nice trick.
Yes.
Does this mean as well that there are certain covariance functions that you could implement within these state space models that you could never actually write down analytically because you can't compute the inverse transform or whatever? I mean,
yes, there are many of them, for sure.
But so which are there more of? Covariance, there must be more of them than there are covariance functions. You can always, because your claim is, well, I can always approximate these very smooth covariance functions after a few terms. So assuming that we've got those sort of covered, the reverse isn't really true. So in some sense, is this a broader modeling framework as well, that there are covariance functions we can use here?
But not all covariance functions can be represented as state space models.
Yeah, non-stationary. Well, so stationary.
Non-stationary. Well, I don't know if they can.
Stationary, but all stationary.
There's this infinite differentiability thing that if it's infinitely differentiable.
Assuming we can approximate those and we're not going to worry about that. The rest can.
Well, now we have too many constraints already. So, so given all these constraints, I don't know. They are not completely like the same class, or either one is like subset of each other. So they just have some overlap. So you can represent some covariance functions as state space models.
But that interests me sort of because it's almost like you're able to do maximum likelihood in a model where you can't actually write down the likelihood. Is that right?
I don't know, how do you do that?
Well, that's what you seem to be saying you can do, because if we can't write down the covariance function, I can't write down explicitly the, but you can write down your form of your way of doing the maximum likelihood here doesn't require you to write down the covariance function. So that's, I don't know.
Yes, you don't need the covariance function to write it down.
Interesting. Mike.
So, I mean, one thing I care about a lot is being able to integrate with respect to a covariance function. So, we're doing Bayesian quadrature. The formed covariance function is very important to me. Can you make any statement about how I can integrate with respect to these covariance functions that I can't write down? Is that anything I can possibly do? So, I do a state space model for my integrator, and then the posterior mean for my integral then is the integral of the covariance function times some other stuff. Is that a thing I can do in this framework?
It depends why do you do that integration. So you might be able to do the same thing in this kind of framework, but it might not be integration over the covariance function. It might be something else. So why I do?
Mine wants integration. You want to be able to do the joint prediction of the integral with the underlying function. Is that what you want?
Yeah, that's right. Well, no. Yeah. So conditional on observation of the integral and what posterior integral. Posterior mean for that integral is involves a term that is the integral of the covariance function over the entire domain against the pi against it.
Yes, but okay, I know how you can do it, but because in state space model you can implement integrator by putting one additional state variable there. So you just need to define the state space model so that you have the integral in there, and then you run the thing, and in the end you have the integral solution as one of the state components.
The integral with respect against the covariance. That's against the covariance.
I think you may not need it anymore because you can get
I can just get the posterior mean.
You can just get the posterior mean directly by, in your state space model, augmenting the state space so one of those states is that integral you want, and then doing the Kalman filter inference to get that marginal mean and how that marginal mean is correlated with the other outputs.
So that would actually give me a posterior integral.
Yeah. Yeah.
So you can, integration is very simple state space model. Well, integration is solution to the first order differential equation, right? So you can actually implement that in state space form, and then you just solve the state space model, and that's your integral. So that's what I meant, that sometimes you can reformulate the question so that you don't actually, of course, the covariance function of an integral is, well, the integral of the covariance function 2 times, but you don't need to do that. That's what I meant. So.
Because there's some covariance functions are very hard to integrate as well. So I mean that's another.
Almost all of them.
Yeah. So for Matern, for example, I don't know how have you integrated the Matern?
No,
you can't. Well, you can do the 1/2 and the infinity, but in between it's tricky. So that's another interesting example of the use of this representation, but it's not spatial, of course.
No, that's a problem.
Yeah.
Yes.
You want high dimensional inputs for that integral. Otherwise, you could just do the integral by some other way.
Yes, because you cannot really extend this to other than time-based processes. Of course, you might be able to have like a partial differential equations with, and maybe the time direction could be, also in non-zero case, could be handled like this. But well, that's something we could take a look at, but we haven't actually. Yes, please.
Is there no way you can just define an ordering in a high-dimensional space that you can do this?
Well, you cannot, and you cannot define Markovianity in one way. There are several kinds of Markovianities.
Give it some approximation.
Of course, you can.
We're getting different types of integration, different types of Markovianity.
Yes.
How many different mathematics are we generating? Okay. Other questions or comments generally on any of the talks, or thoughts from Simo about other talks? Yeah. I can't remember what. Is it, there we
I think we should have coffee break or something.
Yeah, I was assuming it's coffee break. Yeah, so coffee break now, and then back here in 20 minutes for Mauricio. And just thank Simo again for another great talk.